Everyone. In this video, I would like to continue talking about context-free derivations, but we're going to focus on something called ambiguity. Recall that a context-free grammar is a four-tuple, which consists of V, the non-terminals, sigma, the terminals, R, which is the set of rules, and S, the start symbol. Now, we've talked about grammars. We've also talked about automata. So with automata, we think of them as recognizers of strings. They accept or reject certain strings. You just go through the circles and check the arrows and see what happens. Grammars are more like generators of strings. So you begin with the start variable, you choose a rule to apply, you identify a variable, which we're going to use the leftmost one, and we're going to repeat. And we're going to stop when there are no more variables, and it should generate a string that you like. Now, grammars are easy to work with on computers because it's text-based notation, whereas automata with their pictures are not so easy to deal with. And so when we're actually writing our computer programs and we need to compile them, we start with parsers. A parser is a program that takes a grammar and given text notation, and it'll actually tell you whether particular statements that you're writing are syntactically correct for your programming language. Parsing is the process of checking that a string is in the context-free grammar. So it's often used for checking that statements are actually in your programming language. When we do parsing by hand, we'll often draw parse trees. A parse tree is a visual representation of a derivation that shows the hierarchical structure of that language. And parse trees have leaves that are labeled with terminals and interior nodes that are labeled with non-terminals. And this is secretly what's happening when you write a program and are checking to see whether it's syntactically correct. And in fact, you can get programs that draw out the trees for you. So rather than recognizing strings, which is what we were doing with automata, we are now thinking about deriving strings. So as I mentioned before, we begin with the start symbol, and while any non-terminals exist, we pick a non-terminal and rewrite it using one of the rules. We actually have to guess at the derivation step. There could be many choices here. So one new thing to think about, well, not that new, is that this is actually non-deterministic choice. And you stop when all you have left are terminals, and hopefully it's a string that you like. Now what we want to talk about in this video is ambiguous grammars. It's possible to generate a string in multiple ways. I already mentioned that you could generate a string non-deterministically. You have to guess which rule that you're getting, and you end up with a string. Sometimes it's possible to do that in multiple ways. Let me show you an example. To understand ambiguous grammars, let's look at an if-then-else statement. I have here this particular input, which is a string, and it's a nested if statement. I can write a grammar for if-then-else statements. So my terminals include the words if, then, else, for, and then like an equals for assignment. My variables are statement, if, for, assign, and the starting variable is statement. And then my rules are for statement, I can replace it with an if, a for, or an assign. If I can replace with if condition, then statement, else statement, or I can replace it with if condition, then statement. So no else there. Looking at the nested if statement, I could look at the inside first because that's an if then else. If y is greater than 0, then do this, else do this. And on the outside of that, I have if x is greater than 0, which does not have an else statement associated with it. On the other hand, I could think about writing if x is greater than 0, then do this, and then y by itself would not have that, doesn't have that else associated with it. Now, in the end, it doesn't matter because you end up with the same string anyway with all of this same tabbing over and everything like that, but it does change how the parsing will work. There are two valid parses for this input using this grammar, so this grammar is ambiguous. So let's look at parse number 1, statement, then if, and then if then else. Then I start replacing with my terminal symbol, so if x is greater than 0, then statement, else, statement, and that statement gets replaced with an if. So that uses the first rule that I have for the variable statement if. The other way to do this is to do an if statement and then not have the else there. Now here, I am going to just do if condition then statement, which is the second one, applying the rule 2 first, and then continue. So this is ambiguous, as mentioned before, because it has two different parses. If we allow some rules about what is what the precedence of order of rules we apply is, then it changes things. But right now there's two different ways to get to that same final statement. So a grammar is ambiguous if there exists an input string for which there are two or more valid parse trees. Now, this is not the same as doing two different derivations because you can get different derivations by doing substitutions in a different order. Ambiguity is equivalent to having two or more distinct leftmost derivations. So one thing that we're going to do is make sure to always replace the leftmost variable first. And if a particular string can be generated in two different parse tree ways, using this leftmost derivation, then we would say that it is ambiguous. As I mentioned, ambiguity does not affect the language itself. A grammar produces a set of strings, so L of G is just a set of strings, and it doesn't matter really how you got there. And an ambiguous grammar can produce strings in more than one way, but that's like having multiple paths through an automaton, and each of those leads to an accept state. So in the end, maybe it doesn't really matter in terms of what we want in the language. Ambiguity specifically means multiple parse trees. And multiple parse trees could mean that we have multiple interpretations or meanings. And if I didn't have that nice tabbing over, it might not be super clear which if does the else go with. Perhaps you think it's going to be one of those and the compiler thinks it's going to be the other one, which is why the tabbing was important in the first place. But depending on how you're writing your program, you might not notice this kind of bug. Or the compiler is going to think, oh, it's totally fine, and it doesn't do what you expect it to. That means in practice, we often care about which parse tree was produced by a parser so that we, the programmers, don't get confused about what's happening. We want it to be unambiguous to reduce confusion. It does turn out that you can have different grammars that end up producing the same set of strings, and you can write them in different ways. Sometimes it's possible to write a grammar which is ambiguous, and then to create a grammar for the same language that is not ambiguous. Let's take a look at this example. I have basically two different grammars that are for the same thing, expression, term, factor. Let's take a look at this grammar, and let's say that we want to produce the string x plus y times z. The starting states that I have, it's e, and I have two different rules that I could apply. So let's say I do e And let's pick times. Now, because I'm doing leftmost, I am going to replace this E. So let's think about what rules we want to replace it with. Well, over here I have x plus y, so I'm going to do plus, and then this is E and E, which are then going to get replaced as x and y. And then over here, for the times z, I can replace that with z. And so that gives me x plus y times z, which is what I wanted. Another way to do this, though, is to do E and replace that with the plus, E plus E. And now to get x, I replace this x, this is a plus, and I need to replace this E. That's where the times comes in. So that's going to be replaced with E times E, which is then y and z. And so you see that either way I get x plus y times z right here and right here. However, I got to it in two different ways. So this grammar is ambiguous. If you use G2 instead, it actually turns out that this grammar produces the same string, but in an unambiguous way. The first rule that I have is E goes to TA, and then the next thing that I can do is I can only replace T with FB, and then F with X, B is empty, and then X plus TA. After that, I want to replace TA to get Y times Z, and so I can do that. I'm going to replace T with FB, F with Y, then going to get times ZBA, Y times ZA, and then A with epsilon. And so in this case, I've replaced the string. And I got the same thing that I did with G1, but I did it in such a way that there's actually only one way to do it. So in this case, this grammar is unambiguous. The grammar G2 is something which is known as being LL1. So this first L means we read from left to right. This second L means that we create a left derivation of the string, and this 1 means that we look forward at most one character. So this is the way that a particular parser might work, is with LL1, and then there are other varieties. You can put different numbers in here. There's LR as well. We won't go into the details of that, but I did want to point out that there are ways to characterize grammars this way. When I talked about G1 and G2, those were grammars that actually produced the same language, but one was ambiguous and the other one wasn't. However, some languages are inherently ambiguous. For example, 0 to the I, 1 to the J, 2 to the K, where I is equal to J, or J is equal to K. This is a language that is inherently ambiguous. And as we mentioned earlier, when we were deriving strings, we had to do sometimes some guessing as to how to get to that string. And so in this case, like this non-determinism is actually inherent to the system. Like some of these languages are inherently ambiguous, and you always are going to have to guess, and there's more than one choice as to how to get there. So I won't talk much more about this right now, but I did want to point out that it was a thing. And so far this video has been about context-free grammars, but of course we can also talk about push-down automata. There are such a thing as deterministic pushdown automatas, but later on we can talk about what the difference is between deterministic pushdown automatas versus pushdown automatas, which may have some non-deterministic guessing as part of it. So that's all I have for you today. Thank you for watching.